In this section, we're going to be reviewing a little bit of matrix theory. If you have taken the linear algebra course and you already know this stuff, but if not, well, this is not hard to pick up. So a matrix, since we will be dealing with systems that are 2 by 2, we're only going to be dealing with 2 by 2 matrices. So a matrix is just going to be a square array. A 2 by 2 matrix is just going to be a square array of numbers, just like this one. Some people like to use parentheses around the array. Some people like to use square brackets. Doesn't matter. So two matrices are going to be called equal. We're going to say they're equal if every single number is the same. So if you have another matrix, then if every single entry is the same, and these numbers over here are called the entries, then the matrices are the same. If you have two matrices, you can add them really easily. We're supposed to have A and B. The way you add two matrices is by adding the entries term by term. So the entry in the upper left corner, you add it with the entry in the upper left corner of the other one. So that means in this upper left corner, you would have A11 plus B11. And for the upper right corner, you would add A12 and B12, and that would go in the upper right corner, and so on. So you just basically add the entries in the corresponding spot. And these indices have a particular order. So the first index, so this is not an 11, this is a 1, 1. The first index represents a row, and the second index represents a column. So 1, 1 means first row, first column. This one, 1, 2 means it is on the first row, but in the second column. And A21 means is in the second row, but in the first column. And A22, second row, second column. Okay, multiplying uh, a matrix by a real number is also very easy. If you're multiplying a matrix by a number such as 5, then that just means that you multiply every single entry in that matrix by 5. So that's it. It's very simple. To find the product, that's a slightly more tricky one. And here's how you multiply two matrices. So you're going to multiply first the first row by the second column, and you're going to do this um, using the dot product that you learn in Calc 3 or even in trigonometry. So the dot product of two vectors. So this means you're going to do A11, comma, A12, dot product with B11, B12, and that means A11, B11 plus A12, B12. Oh, sorry. That was supposed to be B11, B21. These are 2-1. These are 2-1. So I copied that wrong. But it was B11, B21. So these are 2. These are 2-1. All right, and that's it. And this result goes in this corner, and you can see it's because if this line right over here, you see the intersection would be this corner. So that means that's the result of that dot product is the number that goes in that corner. And then you can do, let's say, this one with the dot product of that one, oops, the dot product of this row and this column, and that would be, if you move this line over here, that would be right there, and you see that the intersection will be this upper corner. So that means whatever I get from that dot product is going to go right here. Then you're going to do this row and this column. And if you move to this line over here, you would see that the intersection is in this lower corner. So that means the result of the dot product of that and the dot product of that goes here. And lastly, if you do the dot product of the last row and the last column, if you move that line over here, you would see that their intersection would be this lower left corner. So the result of that dot product will be right there. Okay, and that's how you multiply matrices. Two by two matrices. So we're gonna do some examples like that where we do all these operations in a minute. But another thing you could do with matrices is multiply them by a vector. And in linear algebra, we usually write vectors um, in the form of a column like this. In calculus, um, and in pre-calculus, like trig, we usually write them horizontally, but in linear algebra, it is customary to write them column-wise. So we have these two-dimensional vector x1, x2, and you can multiply a 2 by 2 matrix by a vector, and that is just the dot product of each row with that vector. So the dot product of this row with that is going to be a11x1, a12x2, and that goes on the top. Then the dot product of this row and this column would be a21x1, a22x2, and that goes on the second entry. This is going to be also a vector. Okay, that's a vector. So the product of a matrix and a vector is a vector. The identity matrix is usually denoted by I for identity, and is a matrix that has entries 1, 0, 0, 1, or ones across the column and 0 on the other one. Sorry, not across the column, across the diagonal. Ones across the diagonal. This is called the main diagonal. Um, and then zeros on the other two places. And it is called the identity matrix because it doesn't really do anything. When you multiply any matrix by I, it just gives you any matrix by I. It doesn't change the original matrix. So A times I is A, and if you multiply by I on the other side, you get the same thing. I times A is A. That's true for all matrices. Okay, now let's do an example where we do all these operations. So we're gonna first multiply. So this is A, this is B, that is X. We're gonna find AB, BA, 3A plus B, and BX. So let's start by computing AB. That means we're gonna multiply 1 plus I, negative 1 plus 2I, 3 plus 2I, 2 minus I, and then we're going to multiply that by the matrix B, which is I, 3, 2, negative 2I. Okay. So it is a dot product first in this corner, the dot product of the first row and the first column. So this is going to be 1 plus I times I, and then negative, so plus negative 1 plus 2I times 2. Then on this corner, it would be the dot product of the first row, second column. So it's going to be 1 plus I, times 3, second column, so times 3, plus negative 1 plus 2I times negative 2I. And now let's do the last two entries. So it would be the dot product of the first row with the second row with the first column. So it would be 3 plus 2i times I. So 3 plus 2i times I. And then dot product of that, and then the product of that with that, which is plus 2 minus I times 2. And then in this corner, it would be the dot product of the second row with the second column. So it would be 3 plus 2i times 3 plus 2 minus I times negative 2i. 2 minus I times negative 2i. Okay, now we just distribute these things. So distribute in here, you would have I plus I squared. I plus I squared, but I squared is negative 1, so minus 1 or plus negative 1. And then distribute in here, this will be plus negative 2 plus 4i. Okay, now let's do this one. Distributing these 3, you would have 3 plus 3i, and then that would be negative and negative is going to be positive, so positive 2i, and then this would be negative 4i squared. Negative 4i squared. I squared is negative 1, so negative 4i squared. I squared is negative 1, so we just write negative 1. And then now here, this is going to be distributing 3i plus 4i plus 2, plus 2i squared, but really 2i squared is negative 2. 2i squared is negative 2. And then plus 2, that's a 4 minus 2i. 4 minus 2i. 4 minus 2i. And then for here, this would be 3 times 3 is 9 plus 6i. And then that would be plus negative 4i. And then this would be negative and negative. Negative times negative is positive. So it would be positive 2i squared. So positive 2i squared would be that. 2i squared is 2. I squared is negative 1. So there. And then simplifying by collecting like terms, you will get, let's start with the real parts first. Negative 1 and negative 2, that would be negative 3. I and 4i is 5i. Now this corner, this will be 3 and positive 4. 3 and positive 4, that would be positive 7. And then 3i and 2i, that would be 5i. Now here in this corner, you would have 4 and negative 2, that's 2. 3i and negative 2i, that's I. 9 and negative 2 is 7. 6i minus 4i is 2i. So that is the answer. That is the result of A, B. Now let's do BA. This is B, A equals. Now I copy B first. This is I, 3, 2, negative 2i. And then I copy A. 1 plus I, negative 1 plus 2i, 3 plus 2i, 2 minus I. Okay, let's multiply. First row with the first column, dot product. So this is I times 1 plus I, 3 plus 3, 3 plus 2i. Then first row with second column will be I times negative 1 plus 2I plus 3, 2 minus I. Then second row with first column, 2, 1 plus I, negative 2I, 3 plus 2I. And then second row, second column, 2, negative 1 plus 2I, minus 2I, 2 minus I. Okay, now we can finish this off in 2 steps. So distribute here, this would be I times 1 is I, plus I squared, but I squared is negative 1, plus 9 plus 6I. Then over here, this will be negative I plus 2I squared plus 2I squared. I squared is negative 1, so plus 2I squared should be minus 2. Then plus 6 minus 3I. Now to that corner, that would be 2 plus 2I minus 6I plus 4 plus minus 4I squared. Minus 4I squared minus 4I squared. I squared is negative, so you would have minus 4 times negative 1. So it will be positive 4. And then here, we have minus 2 plus 4I minus 4I. And then you would have positive negative 2I and negative times negative I. That would be positive 2I squared. Positive 2I squared. I squared is negative 1, so it would be negative 2. And this simplifies to collecting real terms, that would be 8. I and 6I, that would be 7I. Collecting real terms here, that would be 4. And imaginary parts would be, that would be a negative 4I. Then here, collecting like terms, you would have 6 minus 4I. And then 4I and negative 4I, those cancel. You have negative 2 and negative 2, and that's negative 4. And you can see that we didn't get the same thing because the order does matter. AB is not the same as BA. Okay, now we're going to do 3A plus B. Let me draw a line here dividing this. Okay. We're going to do 3A plus B. So this is 3 times A. So I copy A. 1 plus A. 1 plus I. Negative 1 plus 2I. 3 plus 2I. 2 minus I. Plus B. 1, 3, 2, negative 2I. Okay, multiplying a matrix by a constant, which is this one, multiplying by 3, it means that every entry gets multiplied by 3. So I multiply everything by 3. So this is going to be 3 plus 3I, negative 3 plus 6I, 9 plus 6I, 6 minus 3I. So everything gets multiplied by 3. Then I copy B. So that's multiplying a matrix by a number. Every entry gets multiplied by the number. And then lastly, for adding two matrices, you just add the corresponding entry. So the upper left corner with the upper left corner gives me the upper left corner of the answer. So I'm just adding 3 plus 3i plus I, so that would be 3 plus 4i. Then 3 plus, and then upper right corner with upper right corner, negative 3 plus 6i plus 3, that would be just 6i. 9 plus 6i plus 2 would be 11 plus 6i. And then lastly, 6 minus 3i and negative 2i, that would be 6 minus 5i. And that would be the answer for that. Okay, now we're going to do bx. So copy b. This is I, 3, 2, negative 2i. And we're multiplying it by 2, 1 plus i. Okay, dot product of this row with this column, so that would be 2i plus, and then multiply 3 times that, 3 times that, 3 times that. I'm going to do it multiplying next step. And then dot product of this row with this column, so that would be 4 plus negative 2i, 1 plus I. Okay, now this is 3 and 3i, so the result would be 3 plus 5i. And then here you would get 4 minus 2i, so that would be 4 minus 2i, and then you would get negative 2i squared, and simplifying that is 3 plus 5i, and then I squared is negative 1, so this will be plus 2, and 4 and plus 2 is 6, and then you get 6 minus 2i, and that's the end. Okay, so that's how you perform all the operations. You have to be really careful with so many numbers and things going on, but if you're careful, it's not hard to do. Okay, another thing that you could have is matrix functions, meaning these are matrices or vectors where the entries are not just numbers, real numbers or complex numbers. The actual entries could be functions. So we call them matrix functions. And so for example, you could have a vector where the first entry is a function named x1 and the second entry is a function x called x2. So you get both are functions of the same variable t, and then you can call the whole vector, let's say x, and then that would be a function of t. If you plug in t in x, that means you plug in t in the first entry and you plug in t in the second entry. And similarly for a matrix. You could have a matrix where all the entries are functions, typically of the same variable. Yes, of the same variable in here. All right, now, since it is a function, you can discuss all the common function concepts such as limits, continuity, derivatives, and all that. Limits, you basically, for taking limits, you learn this in Calc 3 as well. To take the limit of a vector function, you just take the limit of the individual coordinates or the individual entries. Same for a matrix. If I want to take the limit, I just find the limit of the individual entries. And you also learn that a vector function is continuous in Calc 3 if each of the entries is continuous. Same is going to be true for our matrix. So this matrix function is continuous if all of these are continuous. And also differentiability, you learned that in Calc 3, the derivative of a vector valued function, you just take the derivative of the corresponding coordinates. So same for a matrix function. To find the derivative of this, I just take the derivative of that, the derivative of that, the derivative of that, and the derivative of that. So we have this formula here, which is a true. The derivative of a, so a prime of t, and you can write it like this, is going to be the derivative, the matrix consisting of each of all the derivatives of each of the functions. So you can do everything term by term. And lastly, you can also talk about integrals. If you want to find the integral of a matrix function at over the interval from a to b, then so you can write it like this, the integral from a to b of at dt. That will be just the integral of each of those entries from a to b with respect to t. So basically, you can do everything entry-wise, so coordinate-wise. And you learned that also for vector value functions of a real variable. And you learned that in Calc 3. You could, to do the integral, you can do the integral of each term. All right, so since you can talk about derivatives of matrices and vectors and all that, you can also then talk about differential equations involving matrix functions and vector functions. So this example says, verify that the given vector satisfies the given differential equation, meaning basically you have this differential equation right in here. So it is a derivative of this matrix equals this matrix times that. So that's a legitimate differential equation. But now instead of just functions that are real valued, these are going to be matrix valued functions or matrix functions. And we're going to learn later that this differential equation really is a shorthand for a system of differential equations. That's basically it. But it often happens that solving systems of differential equations is easier or more amenable to do it using matrix notation or matrix methods, linear algebra methods. Right, but anyway, so you have this differential equation. The question is, show that this vector is a solution of this differential equation right here. So this x is a solution of this differential equation. All right, so this is just a matter of checking that when you use this x and you plug it in there, this works, right? You get something that is true. So okay, the easiest way to do this is to rewrite x just a tiny little bit. I mean, you don't have to do this, but it makes it easier. Oops, that should be it too. E to the 2t, to write it like this. So this is a number. Normally numbers, when you multiply a vector by a number, normally you write the numbers in the front, but sometimes in difficult, we write the functions on the set I mean, these are numbers, so normally you write numbers on the left, not on the right, but in difficult it's usually more common to write the numbers on the left because these are numbers that are actually arbitrary, so you have a t, so it's a function. So anyway, so we multiply this vector by this number, so it means you multiply each of the entries by that number. So this is 4 e to the 2t, and then this is 2 e to the 2t. So that is x. Now, if that is x, though, then the derivative of x, and you can write parentheses t there if you want to, is just take the derivative of those. So the derivative of that is going to be 4 e to the 2t times 2, so that's 8 e to the 2t, And then the derivative of that is going to be 2e to the 2t times 2, so that's 4e to the 2t. So that is x, and that is x prime. All right, and now we're going to check that when you use this x and x prime, you get to this one, you get something that is true. So the left-hand side of this equation is x prime, and we just found out that x prime is 8 e to the 2t 4 e to the 2t. Okay, so that's the left-hand side. Now let's see that the right-hand side is also, it's actually the same thing. So the right-hand side is 3, negative 2, 2, negative 2 times x. That is the right-hand side. So this is 3, negative 2, 2, negative 2, and then x is this. So this is 4 e to the 2t, 2 e to the 2t. Now let's multiply this matrix by that vector. So we get 3 times that, so that would be 12 e to the 2t. Remember, it's a dot product of this row with that column. So 3 times that, and then negative 2 times that, that would be minus 4 e to the 2t. Now dot product of the second row with that column, so it would be 2 times that, so it would be 8 e to the 2t. And then negative 2 times that will be negative 4 e to the 2t. And then simplifying, these are all like terms, so you can combine. This is 8 to the 2t, and 8 minus 4 is 4 e to the 2t. So actually then, this is actually precisely the left-hand side. So you get the right-hand side equals the left-hand side. So that means this is, the equation is indeed satisfied. That means that this is a solution of that differential equation. Now we're going to do another one, slightly more complicated, but same principle. Now we're going to check that this is a solution of this differential equation. All right, so let's start by simplifying x. By writing it as a single vector, because you don't really have to do it, but it makes calculations easier. So let's distribute here. So multiply this vector by this number, so it'll be e to the t 0. So I just did this part, and then plus multiply the 2 by that, so it'll be 2 2 t e to the t, and then distribute that one, so it'll be 2 t e to the t, 2 t e to the t, and then this is 2t e to the t. And then simplifying, this gives us that x equals, now add these two vectors, you add entry-wise, so this will be e to the t plus 2t e to the t, and then add the bottom, so 2t e to the t, and that is x. Now we have to find x prime, so we can plug it in here. So x prime is going to be the derivative of that. And then to find the derivative of this, you have to use the product rule. The bottom is exactly the same, so once we do it for that, we can just copy the same thing we get on the bottom. But the product of that product rule gives me the derivative of the first, which is, I'm using 2t as the first, and then et as the second. Derivative of the first times the second, plus the first times the derivative of the second. And that's it. The root of the first times the second plus the first times the root of the second. And that same thing goes on bottom. So 2 e to the t plus 2t e to the t. And we can do just a slight simplification here by adding these two that are like terms. These will be 3 e to the t plus 2t e to the t, 2 e to the t plus 2t e to the t. Okay, so that is x prime, and now let's compare. You can start with either side. In the previous example, I started with the left-hand side and then did the right-hand side. You could do either side first. I'm going to do the same thing. Left-hand side is x prime. Okay, and then we found x prime to be this. Okay, so that's the left-hand side. Now, what is the right-hand side? It's supposed to get the same thing. The right-hand side is this thing. So I'm just going to copy that. 2, -1, 3, -2, x plus 1, -1 e to the t. Okay, so this is 2, 3, -1, -2, and then what is x? X equals this. Sorry, this one simplified. So times e to the t plus 2t e to the t, 2t e to the t, plus, and then actually this one right here, we can distribute, so multiply, so this is e to the t, negative e to the t. And now let's do this product of this matrix by that vector. So dot product of the first row with that column, so this is 2 times e to the t plus 2t e to the t minus 2t e to the t, and then 3 times e to the t plus 2t e to the t minus 2 minus 4, we multiply, minus 4 t e to the t, and then this is e to the t minus e to the t. Okay. Now, two more steps. We're going to distribute this and combine. So this is going to be 2 e to the t plus 4 t e to the t minus 2t e to the t, 3 e to the t plus 6t e to the t minus 4 t e to the t plus e to the t negative e to the t. And now I just combine like terms. We're adding that, we're simplifying that, but also adding this one. So we can add the 2 e to the t and this e to the t, that's going to give us 3 e to the t. And then adding these two, which are like terms, you're going to get 2. You're going to get 2t e to the t. And then here, this 3 e to the t negative e to the t will be 2 e to the t. And then combining these two like terms right here, you get minus 2t e to the t. Sorry, you get positive, because 6 is bigger than -4. So 6 and -4 gives you positive 2. And then you compare, and that is exactly the left-hand side. That is exactly the left-hand side. So that means this actually satisfies the differential equation. It is a solution of the differential equation. So, I mean, we are going to want to learn how to solve differential equations, how to find solutions of differential equations like that and what they actually mean. For that purpose, we're going to need to talk a little bit of systems of linear equations, and this is some stuff, again, that you learn in linear algebra. Okay, if you have a 2 by 2 matrix, call it A, then a real or complex number, lambda, is going to be called an eigenvalue of the matrix A if, when you compute the determinant of A minus lambda I, you get 0. When you compute the determinant of A minus lambda I, you get 0. If lambda is a number that satisfies this equation, that is called an eigenvalue of the matrix. The equation itself, once you write out what all that means, is going to be a polynomial in lambda. In our case, because it's a 2 by 2 matrix, it's going to be a quadratic polynomial. And that quadratic polynomial is called the whole equation is going to be called the characteristic equation of the matrix A. And the polynomial is called the characteristic polynomial. The polynomial that resolves on the left-hand side when you do this calculation. Now, it is a theorem that when that happens, there is a vector. There is a vector, more than one vector actually. But any vector that there's going to be at least one vector that satisfies this equation for lambda. So a vector x is going to be called an eigenvector for lambda. So the x is associated to lambda if, when you put it in this equation, ax minus lambda x, that's true. So ax is going to be a multiple of x by lambda. The multiple is actually lambda. So any vector that satisfies that equation is called an eigenvector. All right, so let's do the first example. Find the eigenvalues, and once you find the eigenvalues, find the corresponding eigenvectors for these matrices. So start with this one. So we're going to find the eigenvalues of this. That means those we're going to find the numbers lambda such that the determinant of A minus lambda I equals 0. Okay, we want to find lambda such that the determinant of A minus lambda I equals 0. And before we do that, I have here some remark. Note that because these are, you're going to be doing A minus lambda all the time, because of that equation that we have to solve when we want to find the eigenvalues. So it's not a bad idea to check what happens in the abstract in general. So if you have a matrix A, it's say A11, A12, A21, A22, and you have a number lambda, what happens when you compute A minus lambda I? Well, substitute in A and what it means lambda I, which is lambda times the identity matrix. Simplifying this part, you're going to get lambda, because you multiply all the entries by lambda, 0, 0, lambda. And then you subtract entry-wise, you're going to get A11 minus lambda, A12 minus 0, so that doesn't do anything, A21 minus 0, and A22 minus lambda. So this is really what you get every single time you write down A minus lambda I. Every single time you write down A minus lambda I, this is what you get. So basically, you start with the original matrix and you subtract lambda across the diagonal, and that's it. So you subtract lambda across the diagonal. So that's what it is. So, for example, then in this one, our task is to solve this equation, determinant of a minus lambda I equals 0. Now, determinant of a minus lambda I equals 0. Now, this is going to be the determinant, and a minus lambda I is just you take the matrix A and you subtract lambda across the diagonal. So this is 3 minus lambda, 4 minus lambda, negative 2 equals 0. No. Oops, I put minus lambda in the wrong spot. Negative, oops. So negative 2 minus lambda. Okay, and now let's find the determinant of this. This says you cross multiply, so this is 3 minus lambda times negative 2 minus lambda minus 4 times negative 1 equals 0. And then let's FOIL this. This is going to be negative 6 minus 3 lambda plus 2 lambda plus lambda squared plus 4 equals 0. This is lambda squared. Combining these two, you get minus lambda, and combining negative 6 and positive 2, you get minus 2 equals 0. So that is the characteristic equation of the matrix. That is a characteristic polynomial of the matrix. All right, then you solve this. Any method you want, we can factor this. So you get that lambda equals 0 or lambda equals negative 1. And those are the eigenvalues. So those are the eigenvalues. Okay. Now we want to figure out what are the corresponding eigenvectors for these eigenvalues. Let's find out what are the eigenvectors for these eigenvalues. Okay, let's start with the eigenvectors for lambda equals 2. Let's figure out what the eigenvector for lambda equals 2. So that means we want to find a vector, and instead of writing x, I'm gonna write v. I kind of like v. We're going to find a v, vector v, such that a v equals lambda v. I like v for vector. You could use x. But we want to find a vector that satisfies this equation. So that means we want to find a vector v, which is going to have two entries, v1 and v2, such that a v equals lambda v. Okay, that's the equation that we have to solve. We already know what lambda is. In this case, we're doing lambda equals 2. So we know what lambda is. We know what a is. We have to figure out the unknown, which is v. Okay, so this is going to be a is 3, negative 1, 4, negative 2. And v is v1, v2. Lambda is 2 in this case. And then v is v1, v2. Okay, so a times v equals lambda, which is 2 times v. It is this. Okay, then you multiply this matrix by that vector. So what do you get? You get 3v1 minus v2, 4v1 minus 2v2 equals, and then multiply here. So you're going to get equals 2v1, 2v2. Okay, and then you have these two vectors, but equal to each other. But these two vectors are equal to each other if the corresponding entries are equal to each other. So these two vectors are going to be equal. That means that the the top number equals the top number here. So that means 3v1 minus v2 equals 2v1, and the bottom number equals the bottom number on the other one. So this is 4v1 minus 2v2 equals 2v2. And then you have this system here. You should simplify this. So you can move the v1, these two v1 to the left-hand side and combine it with that 3. So moving the 2v1 here, you're going to get v1. You're going to get v1 minus v2 equals 0. And similarly, doing that here, you move that on the bottom, you're going to get minus 4. So 4v1 minus 4v2 equals 0. And then note that you get v1 minus v2 equals 0 on the top, and the bottom you can divide it by 4. If you divide the second equation by 4, you actually get the same thing as the equation at the top, and that is actually typical. That's going to happen. That's always going to happen. So these two equations then give you the same thing. And either way, you're going to get that v1 equals v2. All right, so that means then that v equals v1, v2, but v1 is actually the same as v2, so I can replace the v2 by v1, and then I can factor out to the v1 and say that this is v1, 1, 1. And then we choose 1, 1 as the representative of the eigenvectors. So that's going to be our answer. That's the main eigenvector. You can use any eigenvector that is a multiple of that as your answer. So you can use 2, 2, 3, 3, but that is the basic one. And then from this one, you can get any other eigenvector by just multiplying by a random constant, which in this case is v1. That's a random constant. So that means that all the eigenvectors are of this form where v1 is random. Okay? So that means any multiple of 1, 1 is going to be an eigenvector for lambda. So, but we choose a main representative, which in this case, we can choose it to be 1, 1. So that's like a basis for the set of all eigenvectors for that eigenvalue. Now we're going to find the eigenvectors for the other eigenvalue because we had two eigenvalues. Now we're going to do the same thing for lambda equals -1. Okay, we want to find the eigenvectors, or v. So now I'm going to start the whole process all over again. So I'm using the same letters, so you know these are for a new problem. We're going to find the vector v equals v1, v2, such that a v equals lambda v. That's a main equation for the eigenvector corresponding to lambda. Now, writing out what that means, a is 3, A is 3, negative 1, 4, negative 2. And then V is V1, V2. Lambda, in this case that we are in, is negative 1. And then V is V1, V2. Okay, now multiply this matrix by that vector. That's going to be 3V1 minus V2, 4V1 minus 2V2 equals, and multiply negative 1 by that vector, negative V1, negative V2. Now set the entries equal to each other. So you're going to get 3V1 minus V2 equals negative V1. 4V1 minus 2V2 equals negative V2. And then simplifying, if you move the V1 to the right-hand side, to the left-hand side, my bad, to the left-hand side, you're going to get 4V1 minus V2 equals 0. And if you move the V2 to the left-hand side, you're going to get 4V1 minus V2 equals 0. So again, you see that happened. You're going to get the same equation. So you can just, after this point, you can just concentrate on one. That's always going to happen. So what that means either way is that V2 is 4V1. Solving, moving the V2 to their side, you get V2 is 4V1. So then that means that V equals V1, V2. But V2 equals 4V1. And factoring out the V1, you get 1, 4. So 1, 4 could be used as the representative, as the basis for the set of all eigenvectors for that eigenvalue. Okay, now we'd like to do one last example. We're going to find the eigenvalues of this matrix A and the corresponding eigenvectors. So to find the eigenvalues, we have to solve the equation determinant of A minus lambda I equals 0. Now, remember I told you that simplifies to just you take the matrix A and you basically subtract lambda across the main diagonal. So you get 1 minus lambda, negative 1 minus lambda, and then you get square root of 3, square root of 3 equals 0. And then we solve this. So multiply this by that, you get 1 minus lambda times negative 1 minus lambda minus square root of 3 times square root of 3. So it will be square root of 3 squared equals 0. Then before that you get negative 1 minus lambda plus lambda squared, then minus 3 equals 0. And simplifying, you get lambda squared minus 4 equals 0. Combining like terms. Which means that there's two lambdas, and I'm going to use now some notation I think that the book uses. I'm going to use lambda 1 equals negative 2, lambda 2 equals 2. So I'm just basically giving it subscripts. There's two eigenvalues, so I'm going to use subscript 1 and subscript 2 for each of them to distinguish between the eigenvalues. Okay, so now we're going to find the eigenvectors for lambda 1, which is negative 2. And that means we want to find V such that A lambda equals, sorry, AV equals lambda V. AV equals lambda V. Okay, what does that mean? A equal, this is the matrix A, and then V is V1, V2, and then lambda is -2 in this case, and then V1, V2. Then you multiply here, what you're gonna get, first row, first column, dot product, so this is V1 plus square root of 3 V2, then square root of 3 V1 minus V2 equals, and then multiply here, -2 V1, -2 V2. Okay, now setting entries equal to each other, you're going to get V1 plus square root of 3 V2 equals -2 V1. And this one gives me square root of 3 V1 minus V2 equals -2 V2. And remember, these two equations are actually going to give you the same thing. You could work with either one, it's up to you. I'm going to work with the first one. Let me see, which one is the easiest one? Say the first one, to the second one. I think let's work with the second one this time. Okay, working with the second one, you're gonna move that over here, so you're gonna get square root of 3v1 equals -v2. So multiply by -1, you're gonna get v2 equals negative square root of 3v1. And it doesn't matter, you could have worked with the first one, it doesn't matter. So that means then that v equals v1, v2, which equals, now you replace what you one of these two by what you found. We found that the second one is actually negative square root of 3v1, and then factoring out the v1, you get v1 1 negative square root of 3, and we can use this as the eigenvector for lambda 1. And I think the book uses x1 arrow for the notation for that corresponding eigenvector for lambda 1. So we can write x1 arrow equals 1 negative square root of 3. Okay, so we can say that's the basic eigenvector for that eigenvalue. Okay, and now we're going to find the eigenvectors for lambda equals 2, and I'm going to write that in a different sheet of paper. And now we want to find the eigenvectors for lambda equals 2. So find the eigenvectors for lambda 2 equals 2. So we want now the find vectors such that a v equals lambda v, where a equals this matrix. So writing out what a is, you get 1 square root of 3 square root of 3 negative 1 v v1 v2 equals lambda, which we said is 2, v1 v2. We're in this case. And normally you should probably put the index 2 in there. And in the other one, since I'm talking about lambda 1, I should probably put lambda 1 in there. Okay. So either way, now we just multiply here. I mean, that's easy. Just multiply that. You're going to get v1 plus square root of 3v2, and then square root of 3v1 minus v2. And then multiplying the 2 by that, you get 2v1, 2v2. Okay, now set the entries equal to each other. You get v1 plus square root of 3v2 equals 2v1. Square root of 3v1 minus v2 equals 2v2. Alright, again, they give you the same thing, so you can work with either one, whatever looks easiest. I think the second one again gives me the easiest thing because, well, maybe the first. Let me see. Let's do the first one now. The first one gives me square root of 3v2 equals v1. Alright, so then v is going to be v1, v2, but now we replace v1 with square root of 3 v2, v2, factor out the v2 and you get square root of 3, 1. v2, again, v1 and v2 are arbitrary, so this one is going to be the basic representative of the eigenvectors, and using notation in the book. Is that. By the way, the notation in the book is actually not a subscript, it's a superscript. So it should be this equals square root of 3, 1. So the eigenvector corresponding to second eigenvalue is square root of 3, 1. So let me make the change here in the other one. Yeah, the notation used in the book is a superscript. So that should be, this one should be okay. Finally, we talk how matrices can be used to encode systems of linear equations. So if you have a system of linear equations, let's make something up here, such as, I don't know, 2x plus 4y equals 10, and then x plus 7y equals 15. Suppose you have that system of linear equations, you can always rewrite this system in terms of matrices and vectors. Actually, you can write the system in terms of matrices and vectors. So you could write this, the left hand side, like this: 2, 4, 1, 7, x, y. So note that the left hand side is actually exactly the same thing as this, because if you multiply this matrix by that vector, you're going to get 2x plus 4y, and that will be on the top entry. And then this will be 1x plus 7y, and that will be on the bottom entry. Equals 10, 15. So then this is exactly the same thing as that, but written in terms of matrices and vectors. And following the same pattern, you can make any system of linear equations into an equation with matrices and vectors. All right, so in particular, if you have a system of linear equations like this, by just picking up these coefficients, that you could write that as your matrix A, and picking up the variables, that could be your vector x, and then these numbers right here, you can denote that vector by b, so b1 and b2. So you can write then the system like this. A x equals b, where a is the coefficient, this is called the coefficient matrix. Then x1, x2, which are the variables in this system instead of xy. The variables here are x1 and x2. So you can write that as your vector x equals x1 and x2, and then these numbers over here, that's your b. When these two numbers here are 0, that is called a homogeneous system. If that vector b or b1, b2 is not 0, then it's called a non-homogeneous system. We say that a matrix is non-singular if the determinant is 0 of the matrix, if the determinant of the matrix is 0. And in that case, the system has no solutions. This linear system of equations has no solution. If the matrix is singular, we say that the matrix is singular if the determinant is not 0. And in that case, the matrix is invertible. That means the inverse exists. And the inverse is just going to be another matrix denoted by a to the 1, such that when you multiply it by the original one, you get the identity matrix. And now there's a little typo here, that should be a to the negative 1. On either side, you get the identity matrix I. And in this case, then you can figure out what the solution of the system is. If this is your system, and these are vectors, and if A inverse exists, then you can multiply both sides of this equation by A inverse. Oops. On the left, and remember the order here does matter. And then moving parentheses around, this will be a to the negative 1a. This by associativity, you can move parentheses around. Then these two give me the identity matrix, and the identity matrix doesn't do anything. So you get x bar, x arrow equals a to the negative 1, b arrow. So that means you find your x. This is the solution of the system. So if the matrix is invertible, meaning that the determinant is not 0, then this is the solution. You have a formula for the solution of the system. And note that that formula gives you the solution of the system. There's only one solution to the system if the matrix is invertible. If the matrix is not invertible, then the system either has no solution or has infinitely many. You have to work out which case it is. Now, how do you know that a matrix is invertible? Again, it's just by computing the determinant. If the determinant is not 0, then the matrix is invertible. Okay, so what if you know the determinant is not 0, so the matrix is invertible? Then how do you find an inverse? Well, in general, there is a procedure that you learn in linear algebra. For the 2x2 case which we're interested in, we're not going to go through that procedure. There's just a little formula that you can use that is very, very quick and easy. And here's the formula for finding the inverse. If you have a matrix A, B, C, D, and you figure out that the determinant is not 0, so that means it is invertible, the inverse is just going to be 1 over the determinant of A, which you figured out because you computed this to figure out that the inverse exists. And then you change the entries around a little bit. The entries in the main diagonal are flipped. So instead of AD, you have DA. So the entries in the main diagonal, you flip them. And then the entries on the other diagonal stay exactly in the same order, but you change the signs for both. So flip these two and change the signs of the other column. So flip the entries in the main diagonal and change the signs in the other diagonal. That's it. That's usually a little formula that is worth memorizing. Okay, 1 over the determinant, flip the entries in the main diagonal, and change the signs in the other diagonal. And this formula only works for, this particular formula for 2 by 2 matrices. All right, so let's use the formula real quick to figure these ones out. Figure out whether each of the following matrices are invertible, and if they are invertible, what is the inverse? Okay, figure out whether they're invertible, find the determinant. The determinant of A in this one is 2, 4, 3, 1. So, of course, multiply, so this is 2 minus 12, which is negative 10. So that means this is invertible. And if it is invertible, what is the inverse? Well, the inverse is 1 over the determinant, which is 1 over negative 10. And then you flip the entries along the main diagonal. So this is going to be 1, 2. And then the entries in the other diagonal, you leave them the same but change the sign. So negative 3, negative 4. And that is the inverse. That's it. We normally distribute this number right here to give the answer as an actual matrix. So this will be negative 1 over 10, positive 3 tenths. Multiplying that, you get 2 fifths positive, and then negative 1 fifth. Okay, and that's it. I just distributed the negative 1 over 10 and simplified. So that's the inverse. Okay, how about this one? Determinant, what is the determinant of this one? Determinant of 0, 2, 4, 1. So this is 0 times 2, that's 0, minus 4 is negative 4. Okay, so this one also is invertible because the determinant is not 0. What is the inverse? The inverse is 1 over negative 4 times, now you flip the entries in the main diagonal, so this is 2, 0, and the other ones you leave them the same but change the signs, negative 1, negative 4. And then you distribute to simplify. This is negative a half, positive 1, positive a quarter, and 0. Okay, and then the last one, is this invertible, yes or no? Let's find the determinant. Determinant for 2, 6, 3. This is 12 minus 12, which is actually 0. So this is not or non-invertible. So this matrix does not have an inverse. So if you had a system that has these numbers as coefficients, this system either has no solution or has infinitely many solutions. It doesn't have a unique solution, like in the invertible case.